So this is going to be a little tutorial on how to write C programs that can have multiple processes. So you can take your single program and split it up into multiple processes to do perhaps computations that need multiple cores working on the problem. So this is kind of related to an assignment we're working on this week where we're experimenting with multi-process programs. And I thought I would do something similar. So really kind of the first trick is to figure out a problem that a problem which needs to have multiple processes working on it. Because we got computers that are so fast now that really even it's something simple like I want to search through a file that has 15 million lines in it, it just takes a couple seconds to do. So we really need a problem that's going to require us to go through the trouble of creating multiple processes in the first place. And usually such problems are computationally intensive ones, like ones that are factoring prime numbers or doing kind of cryptography stuff. So I thought maybe that prime number factoring problem is what we should tackle here. So the problem description is basically going to be, we've got a file with hundreds or thousands of numbers in it, and we want to know which of those numbers are prime or not. And actually chances are most of them are going to be not prime, just because most numbers are. But we could do something like for each one of the prime numbers, print out all the factors. And so these are kind of computationally intensive tasks, because the easiest way to compute whether a number is prime or not is to run through a loop and just start dividing it. And if you ever if you run through the whole loop and you find that there are no divisors, then you know it's prime. And if along the way you do find some divisors, then you can just print them out. So the first thing to do would be to just write a simple program that does this computation on all these numbers, and we'll just time it and see how long it takes. And I'm starting from scratch here. What you see on the screen is what I've got. I have not pre-planned this in any way as far as typing out the programs ahead of time. I'm just going to do it live right here, and along the way you're going to see all the mistakes that I make, and sometimes I got to look up some documentation online, so I've got a web browser back there, and it's just going to be watching me code. And so if you have any questions, you can just post them on the chat, or you can break in. If you've got a microphone and a headset, then you can just talk. And so away we go. So maybe the first thing to do is just write a simple program where I type in a number and it just prints out all the factors of it. This is a simple program. So that would just be a simple little loop that goes from probably 3 up to the number by 2s. Now the reason why I go by 2s is because, well, should I do that? No, we won't do that at all. We'll just run from basically 2 to n and printing out all the factors as we go. So let's call this factor. The reason why we're doing this is to kind of establish a baseline. What's the worst possible runtime? Well, how long is this thing going to take if we don't do any optimization at all? And then we're going to see if we can make it go faster by splitting up the work amongst multiple processors. So let's go int main int argc. This is the usual C main header. And then we'll input a number. So we'll go like int n printf. Actually, yeah, we'll do this. Enter a number. So this will be a integer. And then now we're just going to write a little loop here. For int I equals 2, I is less than n, I plus plus. So we'll go if n divided by, we'll go n modulo I is equal to 0. So that means if I divides n, then we'll just simply print out the value of I. I guess I'll put a space after it. And then that should be it. So enter a number, 81. There, 3, 9, and 27. Those are the factors of 81. How about just type in a random number here? Okay, that apparently is a prime number, because there were no factors. Let's try another one. Let's make this one even so that we know there's going to be at least one factor. There we go. So you see, this is pretty fast. Let's try boosting the size of the number. So a 32-bit number can go up to 2 billion-ish. So let's go. That's too many. Oops. Let's see. This is about 2 billion. So let's go. Boom. There. 236, and then these bigger numbers. So those are the factors of that. Now, we can actually optimize this a little bit because we don't really have to go all the way up to n. The highest factor this could ever be would be half of n. So let's change this to go up to n divided by 2. Recompile it, run it again. Let's put in that same number. There. Oh, okay, so this is what I thought might happen here. Notice that it didn't print out that factor. And the reason for that is that we divide by 2, but we're only going up to like 1 less than that because of the less than sign. So we really need to make this less than or equal to. We'll try it again. There. Now we got them all. So if we put, actually I want to change this so that I just put the number as a command line argument. So I don't have to type in the number. That'll make it actually easier to run the program. So rather than asking me to enter a number, what we'll do is we'll take the first command line argument and we'll just convert it to a number. So we can use that. We can use scanf for that. Int n scanf or v0 %d there. Now I can just type in the number right on the command line, and that didn't work. Why didn't that work? Int n scanf. Seems to me like that should have worked. Oh, did I recompile it? I did. Oh, string format. Yeah. Oh. No. I'm doing this right. Oh, this is not argv0. Sorry, it's just 1. That's why. There we go. Good. Last thing I'm going to do is just make it print out a new line at the end. There we go. Boom, got it. So now we know the program's working. The next thing I'm going to do is I'm going to take the core part of this program, which is this piece right here, and I'm going to isolate that into its own function. So let's make one. Let's call it factor. So it's not, I guess, not going to return anything. It's just going to simply do the computations and print stuff out. So void factor int n, and that's just going to be the core part of this program here, which is these. Oops, come on. There we go. Nope, come on. There. And then I'll take this out, and I'll just call factor. And it's working. Good. Now, what this allows me to do is put this command called time in front, and it will tell us how long it takes. So this program took 5.3 seconds to run. We can do it a couple more times just to get an average. 5.3. Okay, let me just write that down so I can remember it. 5.33 seconds to factor a number without any optimizations other than just stopping at n divided by 2. Now, I guess the next thing to do would be to generate a file of random numbers that we're going to factor, so that we get this program that takes you know, a fair amount of time to run. So let's call this rand_nums. I don't really need to type a program. I could just type some random numbers. Let's just do that. It's ridiculous. Let's just call this nums. Let me just type some numbers. There's one. There's another one. Too many nines in there. There's another one. Let's see, how big are these numbers? 1, 2, 3, 235 million. There. That's as big as you. No, that's actually bigger than you want to get them. There. You can see how random my numbers are. Maybe I should write a program. I'm ridiculously bad at typing random numbers. Character pointer 8. Oh, come on, I can't type tonight. Let's make it generate 10 random numbers. 10. And then let's see, there's a function called random. It returns a long int to us. And then we need to seed it also. So the way we seed this is we go sRandom, and then we pass it a random number to seed it. Sort of a tricky point there is how do you generate a random seed if you're trying to seed a random generator? So you really only need to sort of seed it with a number that's unique. And one way to do that is you could just get the current time. You know, so every time you run it, basically the time is different. The other thing you do is you could probably pass in like the process ID number, and that's pretty much going to be different every time. This is not the best way to do it, but it'll probably be suitable for our purposes. So let's pass in get PID. And here, let's go along int r equals random, and then we'll just print it out. Is that LD, I think? R. Oops, forgot my semicolon. Get PID, and get PID. I need these two, systypes and unistandard. There we go. Hey, got some random numbers here. Let's see, how big are these? 1, 2, 3, 1, 2, 3. Okay, that's good. That's 2 billion, 1 or 2 billion. Good, good, good. Run it again. Excellent. So let's put this into a file. It's called nums. Great. All kind of biggish numbers there. So now we can see, just using a quick and dirty shell script, to see how long this program takes to run. Since it took 5.33 seconds to do numbers about 2 billion, unfortunately, I think it's going to take about 45 seconds to run this. Let's see what happens. So we'll go for I in cat nums do factor $I, done. Here we go. There's the first one. Second one. Third. Fourth. Two of them in a row pretty quickly. 6th, 7th, 8th, 9th, and 10th. I didn't catch how long that took, but I guess it was probably about 30 to 45 seconds or so. Make a little change to this. Let's just get it to print out that number. Printf. And there. So I got it to print out the number that it's factoring first so that we can see its progress a little bit better. All right, so we got this program where you give it a number on the command line. It factors it using a very simplistic method, and we have it going about 5 seconds to do a number that's in the area of 2 billion or so. And incidentally, what computer am I doing this on? So this is a computer with a 3.2 gigahertz i5 processor, and it's got 4 of them, but I'm only using one because my program is single-threaded right now. So the only way to kind of speed this up is to split the task among all 4 processors, or 2 processors, or 3 processors, and get them all working simultaneously on the problem. So let's see how we could do that. So one thing to notice about the file is that to factor this first number here can be done completely independently of the next number. In other words, the results from any one of these numbers doesn't affect the results of another one of the numbers. And that makes the problem parallelizable. that I can now take the problem, split it up amongst multiple processors, and each one of them can go about doing their work at whatever pace they want to do it at, and it doesn't affect any of the other processors. So in the C class, we've learned about a couple of functions that can take a process and split it up. One of them is called fork, that takes a process and makes two where there was one before. And then there's one called exec, which is used to replace a running process with a different process, like to run a different program. And there's one called wait, which is used by the parent process to wait until the children have finished their work. We're not going to use exec in this case because we just want to continue running the same program. We just want to keep, well, actually, yeah, we just want to keep running the same program. Because what we're going to do is we're going to load in all the numbers into an array, and then we're going to fork out a bunch of children to do the work, and then each one of them are going to do work on a portion of the array. So let's first kind of modify the program we've got to read in all those numbers into an array, and then work on them. So I guess let's see. So I'm thinking in my head, what should we do? So in our main program here, rather than just reading in one program and one number and then factoring it, we should read in all the numbers into an array. So maybe what we should do, since we don't know how many numbers we're going to have, is let's make the first line of this file contain how many numbers are going to be, so we know how big to make the array. So we know there's going to be 10 numbers. So the first number is 10, indicating there's going to be 10 more numbers to follow. So I'm not going to get the number off the command line anymore. I'm going to get it out of a file, but I'll kind of use I will use the file redirection to, would that be a good way to do it? Yeah, that's a fine way to do it. So int, let's call this size, and we'll go scanf %d size. So the first number we get off of the standard input will be the size of the array, and then we'll make an array of that size. So integer pointer r, we'll call it. So r equals int pointer malloc size of int times size. So we'll use dynamic memory allocation to make an array that's big enough to hold all the numbers. And then we'll write a little loop here. It goes for int I equals 0, I is less than size, I plus plus, and we'll have it factor ARR sub I. Do it like that. Let's put some braces here because I think I'm going to need them because I want to also print out that number. That was factor, no, ARR sub I. All right, see if it works. Oh. Come on, include. Here we go. That didn't work. Oh, I don't have my loop actually reading anything in. That's kind of goofy. So I need a loop for int I equals 0. Let's do j. J is less than size, j plus plus. Scanf percent %d. There we go. That should do it. Except for my missing ampersand. Here we go. Well, got nothing. What happened there? Let's see. So I allocate the array, and then I have a loop that goes from j to size. And that seems to be okay. Let's put this here. No. So it was that missing printf in the middle of the loop. It was kind of saving up all the printing until it was completely done. By putting that new line character in the middle of the loop, I'm getting it to print out stuff as it's going. So the loop was running, and it was reading in the numbers. It just wasn't printing anything out. So we've had a couple of people join since I started, and I'm wondering, you guys can post in the chat. What do you think so far? And if you haven't found the chat bar on Google Hangouts, there should be like a control strip over on the left-hand side of your window, and then find the icon that represents chat. Click on it, and then you'll get a sidebar that opens up where you can type in stuff. Or you can just unmute your microphones and start talking. What we've got here so far is a main program that does all the kind of administrative tasks, which is reading in the numbers into an array, and then calling factor on each one of the numbers in turn. Factor itself is a pretty small little routine. So now we need to modify this program so that rather than calling factor on each number individually, which means I got to call factor 10 times sequentially, first time on the first number, second time on the second number, and so forth, I want to be able to essentially spawn off. I have 4 processors in my computer, so I want to spawn off 4 factor
trial.
That was interesting. I want to spawn off 4 factor
trial
functions, all at once. I think I might have to mute you. There we go. All right. So that's going to require now creating 4 child processes and then having each one of them work on part of the array. So to do that, here, after reading in the 10 numbers in our file, we're now going to fork off 4 processes. So, well, that's easy enough to do. We can just go fork, 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 and fork. So that gives us 4 children, but we don't know their process ID numbers, so we might want to store those away. So let's go PID T, PID, let's call it 0. One, And I know this might suggest an array, but we'll take care of that later. Okay, so that's going to give us our 4 children, but each one of those 4 children is a complete clone of the parent. And the children don't even necessarily know they're their children because they're clones. They have the same memory, they have the same history. The only thing that lets them know whether they are the parent or the child is what this PID is. So what's going to happen is when the parent calls fork, the parent's going to return from fork and get the process ID of the child. But when the child returns from fork, all it gets is the process ID of 0, and that lets it know I'm the child. And we also got a problem here is that when this fork is called the first time, then the process is split into 2, right? And so we sort of, it's not really this way, it's sort of this way. They come off to the side, and the parent continues down. What am I trying to say here? So the parent gets the process ID of 0. The child gets the process ID of parent gets a process ID of the child, and the child gets a process ID of 0, and so the child knows, hey, I'm the child here, and so if it gets an ID of 0, it should start doing work. And I want it to do work on part of the array. But the question is, how does the child know which part of the array to work on? Because there are going to be 4 children, and they're all complete identical clones of the parent. And so how would each, they only get a process ID of 0 coming back, so how does each child know like which child number it is? Like, am I the first child that got spawned off? Am I the second one that got spawned off? The third one or the fourth one? I don't know. So what we need to do is we need to set a variable in the parent that tells us like how many times we called fork. And because the children are clones of the parent, they'll also have this variable in them. And so they'll be able to look at the value of that variable at the time that fork was called and determine how many times fork had been called. Am I making sense? Maybe it'll make more sense once I put the code in here. So let's make a variable called int forked. And it starts out being 0. And then after the first fork, we go forked equal plus plus. And after the second one, we do it again, third one, and then that's it. So the first time we call fork, the value of forked is 0. Actually, why don't we call this child num? Because it's getting kind of confusing to say fork and forked. Here we go, child number. So the number of children before we do the first fork is 0, then the number of children is 1, then it's 2, then it's 3. And then here we'll say if if PID 0 equals 0 and PID 1 is equal to 0 and PID 2 is equal to 0 and PID 3 is equal to 0, that means I must be the parent. I'm the parent. So all of those process IDs came back being, sorry. That means I'm the child. I'm a child. Let's see, how am I going to do this? Sorry, I'm thinking. Think how to do this. So a couple issues here. I need to know if I'm the parent. So I'm the parent if all of those process IDs are not 0. Okay, so if PID 0 and PID 1 and PID 2 and PID 3. So if all of these are not 0, I must be the parent. I'm the parent. And what I'm going to do is I'm going to wait for my children to finish. And I need to, this is not the complete statement here. It's just there's a placeholder. We'll finish it up in a moment here. So else. So if I'm not the parent, I must be one of the children. So we'll go if, else, if PID 0 is equal to 0 and child num is equal to 0, that means I'm child 0. And I'm going to do some work. But I'll leave that as a placeholder for now. Else, if PID 1 is 0 and child num is 0, then I'm child 1. And we'll just repeat this a few more times. Okay, so this is 2 and this is 3. Oh, sorry, and this is 1, 2, and 3. Okay, so if process ID 0 comes back as 0 and the value of child number is 0, then I must be child number 0. If the value of PID 1 is 0 and child number is equal to 1, then I must be child 1. And the reason why I got this counter here instead of just simply looking at these variables here is because when these PID 0, 1, 2, and 3 variables are created, they kind of have random values at first, you know, because maybe I can do it just with these here, but this gives me sort of an ability to control exactly what these values are. The problem is that, like, let's say child number 1 is forked off. Child number 2 and child number 3 haven't been created yet. So essentially these variables don't exist yet before the fork happened, which means after the fork happened, they have maybe kind of random values in them. So I can't rely on these numbers strictly being 0 or not 0 to figure out whether they're a child or not. So that's why I got this counter over here, this child number. This is giving me some control, saying, yes, for sure, I know this value of this counter is going to be 2 after the first 2 forks have been done, or after the first 3 forks have been done. We'll play around with that. Maybe I don't need that. We'll see. Okay, so if I'm child number 0 and I've got this array of 10 numbers, I really only have to work on 2 or 3 out of those 10 numbers. So I've got an array of 10 numbers. Which one should I work on? Should I work on number, you know what I should do, just for simplicity's sake, is I should add some numbers onto it. Let's make it 16 numbers so that everyone's got the same amount of work to do. Let's make this 16. Okay, now there's 16 numbers in here. Yep, that's good. 16 numbers. So here's the thing. So which of these numbers should child 0 work on it? Should they work on the first 4 numbers? And the second child works on the next 4 numbers. Third child works on the next 4, and the fourth child works on the last 4. Or should it be something like the first child works on this one, and this one, and this one, and this one, So kind of every fourth, and then child number 1 works on this one. I think I'm clicking on the right ones here, and this one. So every fourth, but starting at number 1, and then child number 2 starts every fourth, but starting at number 2. I guess there's no real difference between them. I mean, because it's all independent work, right? So it doesn't really matter. It's just how we're going to do the calculation of figuring out which ones they have to do. Let me think. What's the better way to do this? So we could write a loop where we take the total number of numbers divided by the number of workers, which is 4, and that tells us how many numbers we're going to be doing. So 16 divided by 4 is 4, which means each one of the workers is going to be doing 4 numbers. And then we can write a loop that just counts from 0 to 3, basically, and then we just calculate where it has to start. I think that could work, I guess. Let's go with that. So if I'm child 0, so we'll go like int so the first number I'm calculating is how many lines I have to do. Well, it's called lines equals size divided by 4. Since I know there's 4 workers. And actually each one of the children does the same thing. And then where do they start? So let's go start is equal to well, I know that for child 0, the start is going to be 0. For child 1, the start is going to be 4. And then for child 2, it's going to be 8. So I see the pattern now. So the start is going to be 4 times the child number. Like that. So for child number 0, that should come out to be 0. For child number 1, this should be 4. This should come out to be 8, and then this one should come out to be 12. And then each one of the children is going to do this little loop here. This one. Oops. That's not what I meant to do. Huh, why is it doing that? Nope. Nah, I'll just rewrite it. 4 int I equals 0. Oh, so int I equals start. I is less than start plus 4, I plus plus. And this is just the same code that we had down below. Okay, let me take this out. And then just paste it in a bunch of places. Okay, and I think the code is all written so that every child does the calculation itself and doesn't I mean, other than this number 4 here, which I hope to eliminate eventually, there's no hard-coded numbers in here. So all the calculations are done based on the child number. So I think I'm pretty happy with what I see here. The last thing is, after each child gets done doing the work, it needs to exit, indicating that it's done. Otherwise, it's going to hang around. I mean, literally, children will just hang around, and I'll have lots of children sitting around doing nothing, taking up space on the computer. Okay, and then the last thing here is to do this wait. So the way you do this is, so wait is going to return the process ID of the child that died. So essentially, the parent can't just do one single wait. The parent's got to do 4 waits for all 4 children to go away. So anyway, this is done as int status, pass in status here. And you get a process ID back. PID T child equals wait. But we know we need to do 4 waits, so I'm wondering if I should just call it 4 times, knowing that the wait's going to return 4 times, or what? Well, let's see what happens. I mean, so I got to wait, and then one child is going to return back and say, "Hey, I'm done," and then I got to go wait again and wait for the next child to die, and then wait again, and then wait again. And then when all 4 of them have done their work, then the program is completely done. All right. Oh, that's right. So did that take care of it? Somehow my command line got messed up. There we go. All right. Let's see if it does the work. Oh, you know, I'm going to make a couple of changes here anyway. Let's get it to print out. Print. Oh. Mm-hmm. I was going to get it to like every time we call fork, it should print out like that it did some work, but I don't think so. Interesting. Now this is so a couple of interesting things have happened here. One is, I got the prompt back here, but some of the children are still doing work. And the other was, why did I get these repeating numbers? 1, 2, 3, 4, 5, 6, 7, 8. I got 8 of them. and then 1, 2, 3, 4, 5, 6, 7, 8. I got 8 of them again. And then this one here, I got 1, 2, 3, 4, 5, 6, 7, 8. I got 8 of those. And then I got 8 of those, but there's supposed to be 16 numbers. 1, 2, 3, 4. I got only 4 distinct numbers there. Huh. And then I got 8 of each. And it'd be interesting to see which of those are. So those are 9, 4, 8, 6, 3, and 8, 1. Which was the first one it did? Wait, what? Am I missing something here? Oh, here it is. It's this one. 9, 1, 1, 6, 9. And then 1, 9, 0, 8, 1, 5, 5, 6, 3, which is this one. And then it did this one, and then it did this one. Interesting. So it didn't do any of these up here. Huh. So, and why did it repeat each one of them 8 times? So the number of lines is size divided by 4. And size is 16, so 16 divided by 4 is 4. And then start is 4 times child number. Start to start plus 4. Then I factor it and then print out and that side. It looks okay. So there's 2 perplexing things. One is, why did it only do the last 4 numbers in the file? And the other is, why was each one printed out 8 times? Oh, I know. It's here. This is the problem. The problem is here. Does anybody else see what the problem is? It's kind of sneaky. Think about what happens here. So we call fork once, and after we call fork, there are now 2 processes that are clones of each other. So what happens when we call fork again? How many processes do we have now? Do we have 3 or 4? And if we call fork again, do we now have 4 or, excuse me, we call fork, now we got 2 processes. Yeah, do we now have 3 or do we have 4 processes? And now do we have 4 or do we have 8 processes? And here, do we now have 5 or do we have 16 processes running? Every time we call fork, we're going to double the number of processes. We need to ensure that the children don't call fork. Only the parent calls fork. So to make that happen, we need to do something like, we also need to make sure that the children don't increase the child number. So we do something like if PID 0 equal, if PID 0 is greater than 0, then do this. And then if PID 1, do this. And if PID 2, do this. I think. Still not convinced that's going to solve the problem, but we'll see. I think I'm going to end up making an array here. PID T, so an array of 4 PIDs. And initially, I should probably put zeros in there. So now I'll have a loop. And C equals 0, C is less than 3. C standing for child number. Actually, I got a variable for that. It's called child number. Trying to think how to handle this. Because again, the main problem is that every time you do a fork, you get an exact clone. And so any variables that you set before you do the fork remain to be set. So we need to distinguish between the children and the parent, so that the parent will continue to go on and do forks, and the children won't do that. Because what I want to do is I want to put a fork in here, but I want to make sure that only the parent does that. In other words, only the parent does this loop. Children don't do that loop. And, yeah, I need to wrap it in an if statement, but what would that if statement look like? If I do something like if what is true, then do this loop. So if I make a variable called like int parent equals 1, and then if parent is true, then do this loop. But parent is going to be 1 for the children also. Nevertheless, I think we might be on the right track here. So if parent is true, so what I want to do is I want to set that variable basically false. If not child 0, well, let's see. So this becomes child num equals fork, right? So for the parent, the value that gets stuck in the array is the process ID of the child. For the child, the value that gets stuck in the array is 0. So maybe the thing to do is all the children actually end up going into this loop, but they never actually do any of the forks. So can I do something like if not child num? So if this value is 0, do the fork. Then it goes to the next child number. No, that's not going to work because once the new child gets created, the value in that array certainly is its process ID number. Huh, this is the tricky part. We need some kind of condition that's guaranteed to be true for the parent and false for all the children. Okay, PIDP equals fork. If P then assign it. We'll assign it to the array. And if P is 0, then we're not going to assign to the array. I think you're on the right track there, but that's essentially what it's going to do in the first place. So first of all, are you clear on the fact that when you do a fork, you call it once, but it returns twice? Does that make sense? And since it returns twice, it returns once from the parent, in which the value that it returns is not 0, and the child also returns from it, and the value that it returns from is in fact 0. Oh, maybe we need to do something like this. So we'll go ahead and we'll do the fork, and then we'll go if child num is equal to 0, then let's break out of this loop. Right? So the parent enters this loop. It does a fork, assigns it to the array, and then both the parent and the child look in the array. If the parent sees a not 0 number there, it'll go back up and do the next iteration of the loop. If the child looks in that array and sees a 0 there, then it knows I'm the child and I should get out of this loop and then get on with life. I think that'll work. And also the value of child num at that point will be left at the proper value for each child. So that each child will know what child number it is, because we're going to, after entering the loop the first time, the first child is not going to have child number incremented, so it'll remain at 0. The second time we do the loop, the second child will have that child number bumped up to the next one. So I think this is good. So the next thing is, how do we know that you're the parent? So that we know we're the parent if that entire array is still all zeros. And in fact, we don't have to look at the entire array. We could just look at the first element of the array. Because if we're one of the children, we might as well look at the whole thing. Why not? There's probably a better way to do it, but let's look at the whole thing. Okay, so if all 4 elements of that array are not 0, then I'm the parent, and I should do 4 weights. And this should be child 0. So if first element is 0 and child number is 0, then I'm child 0. Good. All right. That's better. Hey. Okay, we got the prompt back, and then one more child will go, I got one more thing to do. So it almost worked, but that's pretty close. So what was the whole time on that thing? Look at that. Well, okay. A little more than 11 seconds. Let's say 13 seconds. 13 seconds to determine the factors of 16 numbers. And remember, before it was 5 seconds for one number. So extrapolating out, and that was a number that was about 2 billion. So extrapolating out, 16 times that would have been, 16 times 5 is 80 seconds. But they wouldn't all take 5 seconds. Some of them would take less. So let's say it was an average of 3 seconds each. 3 times 16 is 48 seconds. To do the whole, I should have left the whole. I should have kept the whole program. Now I'm thinking about how to refactor the program so that I can make it fork or not fork. Actually, I probably can. Let's let's put in here const int children. So while I'm doing this, would you all agree that this ran faster than if it was just one process running? Oh, this was 3. That should have been 4. Okay, I'm going to have to work on this. This is clearly a problem right here. Let's see if I can just look at 0. I'm also scheming a way to be able to set a variable called parent that's guaranteed to be true for the parent and false for all the children. So I only have to look at one variable to determine if I'm the parent of the child, rather than 4. I'm also seeing a loop right here. I don't feel like making this change anymore. I'll work on it later. I'll leave that at 4. So does this still work? Yeah. Uh-oh, I broke something. Yeah, see? There, are we back to the old behavior? Yeah. Hey, that time, I don't know if that was a fluke, but that time I got the prompt back after the children had done all the work, which is the behavior I wanted. So, well, so do you agree that this program is faster because it's splitting up the work among 4 processors instead of just one processor? So if we think that it might have taken about 45 to 50 seconds to do all 16 numbers with one processor, and this only took 11 seconds to do it with 4 processors, that's about right. That's about 1/4 the time. What I was hoping to do was be able to write the program so I could just change this number here, 4, 3, 2, 1, and that would change the behavior of the program. So if I change that to not just 1, sure, it's going to spawn off 1 child, but then that 1 child has to do all the work. And it's kind of the same as spawning 0 children. I mean, there's a little extra overhead in spawning the 1 child, but it's not much. And the other was, can I condense this program so I don't have this chain of if-else's here. In other words, I want to make it so the program is designed so that I can just change that one variable and it'll do the right thing for any number of children, rather than have these explicitly written in hard-coded 0, 1, 2, and 3s. I kind of don't like that, but I think for the purposes of showing how this program works, I think that's reasonable for at least a kind of a prototype. So the interesting thing would be to generate some more random numbers. Oh, come on. So maybe let's go up to, let's see, 16 is 4 each. So the next one would be 20 would be 5 each. 24 would be 6 each. Okay, good. Cool. So that's able to factor all 24 numbers in. That seemed to go actually pretty darn quick. Total time on that one, wow, 10 seconds. It's even fast. I guess it must be that the numbers are all fairly small. They're they're all like less than a billion. So if we generated a new set of numbers and then factored those, we should get a different time. $12 seconds for that one. So the amount of time is going to differ depending upon the exact makeup of the numbers, but that's a general idea. So if I was to, so here are some things to improve. And I think I've gone over these already, is take out this chain of else ifs. There should be only kind of like one here. So basically, if I'm the parent, do this thing. If I'm the child, do this thing here. But should only be one check for whether you're the child or not. So basically, this is how I'm determining if I'm the child. There should be some other way to determine if I'm the child. Like one single variable that says whether I'm the parent or the child or not. That might be cool to figure out how to do here. Let's see if we can figure that out. Int parent equals 1. So we're going to do a fork. Well, here's a quick and dirty way of doing it. After we get into all this stuff here, let's write a little loop. Int c equals 0. C is less than, what was that called, children? So what we want to do is we want to check, basically, if all those values are 0. So if child C is not 0, so if any of those numbers are, yeah, I'm not liking that. So what I want to do is I want to do something like this. Let's set this to 0. Parent 0. Parent equals 1. Okay, so we'll set parent to 0 initially. Then we'll start doing this stuff. So if we do a fork and then we do a break, we did a break because we were the child, which means we're not going to set parent to 1. But if we're the parent, we'll set parent to 1. So that means I should be able to just say if parent, like that. Oh, there we go. Okay, hope I didn't break anything. Apparently I did. No? Is it working? Yeah, I broke something. So we set parent to 0 initially, then we go into this loop. It should be the only time this gets set to 1. Oh. Yeah, parent is set to 1 after the first iteration, right. So it means child number 2, or child number 1, basically also picks up the parent is equal to 1. You're right. Can I do the reverse? Default to 1, set 0 if I break. Okay. So this starts out at 1. So it means something like this, right? Like that. Okay, we'll try it. Did it do all of them? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Whoops, sorry, I lost my count because I scrolled the screen. Well, let's start from the bottom. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There's only 15 there. Oh. This should not be start plus 4. This should be start plus lines. The number of lines to do. See the problem, well, you see what the problem is there. But that was all initially because I chose 16 as that starting number. It was kind of a, And this is start lines. And that's kind of a lousy number to start with because 16 is 4 squared. So it's both the number of lines to process and it's your number of children. And so if you mix up the variables, you don't know which one you mixed up because their values are the same. They're both 4 and 4. So it's better to start with a problem size of like 20. So the one of them is 5 and one of them is 4. And then it's obvious if something's going wrong. Also, this is hopefully going to give us a longer running time because we got actually more work to do. And it looks like we got more work to do because it's scrolled off the screen. That's good. One, two, three, four, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. I think I lost count somewhere in there. 23, 20, close enough. That's all of them. I'm sure of it. So that means I should now be able to say else if not parent. And there's nothing in this section here that has any hard-coded numbers. It's all calculated from pre-existing values. So if I should be able to get rid of all this stuff. And significantly shorten this program. Now, if this scrolls off the screen, yes, it did, then we know that our change is good. And I don't have a dependency here anymore on initializing this to 0, which I like because that removes that hard coding of the number of children. I think. Let's hope I didn't break anything. Hasn't crashed yet. So good sign. All right. So the next thing to do is look through here and make sure there's nothing left that has anything to do with the number of children except for that constant variable at the top, constant value at the top. And I don't see any. Well, except for this. So we'll go for int c equals 0. C is less than children. C++. Let me just call wait. Wait, what? Spigot expression. So there's this weird thing in C. I think that's what this is like You this appears to be one statement inside the body of the for loop, but it's actually two. Something like that. And there's something about you can't declare a variable as the one thing that you do inside of for. It's actually two things, or something like that. So the way to solve that is to put the braces on there. Even though you've only got one thing to do, it now works. See, that's just it's a weird C thing. I don't think Java has this problem. It's only C that does this. Could be an argument in favor of always putting the braces on there. So I didn't break it, did I? Grind, grind, grind. Yeah, it's fine. Cool. Okay, so now I'm hoping I'll be able to go like 2 right there. And watch it take twice as long. That's a little strange right there. And I saw it again right there. And it's there. So I've got some duplicates. Okay, so the number of lines I need to do is the size, the total number of lines, which in this case is 24, divided by the number of children, which is 2, so I should get 12. And then my starting line number, starting array element number is the number of children, 2, times my child number. Not correct. Because one child should start at 0 and the other child should start at 12. And this is only going to start at 0 and 2. That should be lines. See, another reason not to use square numbers as the size of your data set. I think that's better. Now, why are some of these printing out with nothing after them? Were they there before? Or did we have a bug where it wasn't doing those and now it is doing them? And these, for some reason, are prime. I wonder if that number is prime or not. So I'm wondering if there is a I wonder if there's something where I can just plug in a number, tell me whether it's prime or not. It's a prime number. Okay, so were we missing those numbers before? Let me scroll up here. Scroll, scroll, scroll. All right, so in our previous runs, we were either skipping those numbers, like not doing a chunk of the data set, or we were having duplicate. We were just like, probably were never hitting them because we were starting, yeah. Well, so is that true? Because before I had, oh yeah, that's right. I started out with 16, then I made it 24. Yeah, I probably wasn't hitting those. So we could kind of say that the program is more correct now than it was before, even though it appeared to be working right. So I'll bet you if we went up and looked at these outputs, we might see something like duplicate lines somewhere in there that we missed. I don't know if it's worth looking at them for those problems. There's one. Boom, right there. Duplicate. And you see another one. This one. Well, there should be another duplicate. There it is. Boom, right there. Yep. So now, I hope we don't have any duplicates. I don't see any offhand. So that means put that back up. Did that go faster? I think it did. So if I make this 1, it's still going to spawn off a child, but that child is going to do all the work. Seems to be working. All right, so the next thing I want to do is there's a program called Top that'll let you see how much CPU time processors are using. And right now, there's nothing using any appreciable amount of CPU time. But if we run this program, we should see one factor running using up 100% of one of the CPUs. Okay, now I'm going to abort that early. And then let's make this 4. And now we should see a whole bunch of factors running. There's 4 of them, each one of them using 100% of the CPU. Looks like one of them finished, and then the other 3 finished. And just out of curiosity, what happens if we make this like 6? Will it get faster, or will it get slower? So now I've got 6 running, but each one of them is only using up about 75% on average of the CPU. So it's splitting 6 processes among 4 CPUs. And let's time it. See how long that took. Okay, total time there was 17 seconds. And then if we bring this back down to 4, and run it, now we got four processes, each using 100%. We got total time of 17 seconds. So even if we make it 6 processes, it takes the same amount of time as 4 processes. What happens if we make this 8? So do you have a prediction? Do you think it'll take the same amount of time? Think it'll be slower, or do you think it'll be faster? Eight processes, all using 50%. "17 seconds." But if I make this 2, actually let's make it 2. And then run it. So now we've got 2 processes all using 100%. Mm-hmm. 33 seconds, so about double. So what this tells us is that you get a speed up every time you spawn off a new process, but then you hit a limit. And the limit is the number of CPUs you have. And spawning off more processes than you have CPUs when you have a compute-intensive task like this, where they're using 100% of the CPU, doesn't make any sense. In fact, it has no benefit, or actually, not only no benefit, but it's also no downside. It takes the same amount of time. So why spawn off 8 when you could just spawn off 4? I mean, I suppose you could spawn off 8, but there's no reason to. But definitely you want to spawn off as many as you have processors. Now this only goes for tasks that are compute intensive. If you've got stuff that's disk intensive, like compiling programs or searching for things on the file system, then, well, I shouldn't say that, because then the disk drive becomes the bottleneck. But if you have something that's not quite so compute intensive, then it may actually make sense to spawn off more processes than you have CPUs, because you really the number of processes has to do with CPU utilization, and you want to get that utilization up to 100%. And so if your process is maybe only computing things half the time, 50% CPU, 50% waiting around for something else, then you might actually want to spawn off 8 processes in this case, so that you get a close to 100% CPU. So when you use the make command to compile the programs, there's a option you can pass into make. You can pass in -J and then a number, and that tells it how many sub processes to do in parallel to make on your particular computer. And they recommend actually having that number be 1 more than the number of CPUs you have. So if you've got 2 CPUs, you should make that number 3. And if you've got 4 CPUs, you should make that number 5. And the idea there is that compiling a program is not 100% CPU intensive. There's some disk activity as well, as it reads and writes reads the source code in and writes the compiled program out. And so by spawning off more make or more simultaneous compiles than you have CPUs, you're using the CPU as much as possible. So I would say 5 there, and then the rest of the stuff I want to do, and then I would get 5 simultaneous compiles. Anyway, so that's what I had for you today. It's almost 9 o'clock, so this has been almost 2 hours. Here's the program we ended up writing. This program is able to do simultaneous tasks, to do simultaneous processes to do compute-intensive tasks, which is in this case factoring numbers. I'm looking here in the chat. I was wondering if you guys have any questions. I'm also curious to know what the video quality was. I know the video quality is going to be dependent somewhat on the bandwidth on your end. I'm still experimenting with the Google Hangouts, and I want to know how clear it is. The ideal size that I've got this set to is 1280 by 720. So if you've got the window set to be bigger than that, it's going to be a little blurry. But the question is it at least legible? Downstream is terrible, so the video is pretty bad. Oh, so you mean your own downstream is not good? I see. Marshall says his window is bigger than 1280 by 720, and it's still readable, just a little blurry. So the other option I have is I could capture the whole screen, and that would be a 1920 by 1080, like a full 1080p. But the problem there is that, out of the whole screen, though, my little terminal session would just be a little tiny window off in the corner, and now the fonts would be smaller. So I could then, of course, make the font bigger, but now we're kind of back to the same boat we were in before, which was, there's only so much I can show on the screen. So, should I make the windows smaller and capture a smaller area, or should I make the fonts bigger and capture a bigger area? And also, I've got off to the side, which you can't see here, I have some controls on the computer, and I'd rather not capture those things, I guess. I think, though, that Google Hangouts, when I do this Google Hangouts on air, after I click on end, it's going to upload this automatically to YouTube, and then in a couple of hours, the entire video will be available there for you to watch. So I guess the last thing I could do is I could scroll through this code one last time. So if you're watching that video on YouTube, you can see it on the screen here. There you go. So any last questions? Did you get some benefit out of this? Well, I'll go ahead and click stop here. So the stop doesn't mean that you're going to have to stop chatting. It just means I'm going to stop recording the video. So I'll click stop now, and I'll see you guys later.